Another common question that we might have had problems with in the first semester is looking at recoil forces, explosions. Usually when we talk about momentum and impulse and collisions, you're talking about object A hitting object B and then looking at the aftermath. But an area that lots of students have a hard time with is looking at when something explodes and analyzing the movement of the pieces of that explosion. Okay, and understanding how recoil works, okay, recoil forces. And you can see this guy in this video who's shooting a gun. If any of you have ever shot a gun before, hopefully not many of you, you would experience a surprise in the form of recoil. And this guy was definitely not prepared, holding the gun away from his shoulder. And the explosion causes the gun to fly back, inflicting a lot of force on his shoulders, okay? So definitely bad form, okay? So why does that recoil happen? Well, the recoil happens because of these three things down here. You have Newton's third law, okay? Every action has an equal and opposite reaction. So the force applied on the bullet to thrust it out of the rifle is going to be equal to the force that the bullet applies on the gun, sending it in the opposite direction. That's one way of explaining it. The second way of explaining it is the law of conservation of momentum, which we'll go through in a second. And the third is being able to calculate the impulse and momentum relationship. Okay, what is the force required to push that bullet out at its speed? And applying Newton's third law, that force is going to be equal and opposite, causing the rifle to accelerate backwards. Okay, so these three things would be how I need to be able to state these three things if it ever says explain why that happens. Okay, so if you're ever talking about Newton's third law, you have to remember that Newton's third law looks something like this. It talks about force couples, okay? So you can assume that this guy is A, okay? And the bullet is B, okay? Well, the rifle is somewhere communicating those forces, okay? So the force applied by A on B, all right, is equal to negative BA, all right? And that's Newton's third law in a mathematical form, the equal and opposite reaction. And AB means a force couple. Okay, so all forces have a couple. If I apply my arm to the wall is my arm and the wall are a force couple. That's what that means. So if ever it asks you to define Newton's third law in a question, you have to state what I just wrote over here. FAB equals negative FBA. And that would help you rationalize an answer. So in the rifle, okay, if I pause this, the rifle could be A, the bullet could be B, and the bullet will be applying an equal and opposite force backwards, okay? And then how do we explain this in terms of conservation of momentum? All right, just let me erase all this. Well, the conservation of momentum says that the momentum before and after a collision or explosion is conserved. So the sum of the momentum, remember the symbol for momentum is P, is equal to the sum of the momentum after, okay? Or the sum of the momentum before minus the sum of the momentum after is equal to 0. That's another way of saying it. And that's the law of conservation of momentum. So the momentum of the explosion before is 0 kilograms meters per second. That's the momentum before, because everything is stationary. So if we rewind that, get him to hold the rifle back up again, okay, you can see that as he's holding the rifle up, everything is stationary, okay? The bullet is stationary, the rifle is stationary, so the momentum is 0. That means that the momentum after has to be 0, but there's no way that there's 0 momentum. The bullet is flying to the right, okay, and the rifle is flying to the left, but the sum of those vectors of momentum will sum up to 0, okay? So I can write this out, okay? So the sum of the momentum of the bullet plus the sum of the momentum of rifle, okay, is going to be equal to 0. And that would explain why they go in opposite directions, okay, in order to cancel out. So if an object, remember, is moving towards the right, the momentum will be positive. If it's moving towards the left, the momentum would be negative. And what is the formula for momentum? Okay, momentum is equal to mass times the change in velocity, or momentum is equal to the change in mass times velocity. Those are interchangeable. Okay, that's my change. My change in momentum can be either or. That's a trick that you have to understand. Okay, an object can change its velocity or it can change its mass, and that's going to change its momentum. Okay, so in this case, we're not changing the mass of anything. Okay, we're changing the velocity. All right, so in this case, if I want to look at the momentum, I would need the mass of the bullet times the velocity of the bullet plus, okay, and remember this is actually minus because it's going to the left, the mass of the rifle times the velocity of the rifle. And that's going to be equal to 0. So if you have these variables, if you have the mass of the bullet and you have the mass of the rifle and you have the velocity of the bullet, you'd be able to figure out the velocity of the rifle. On the other hand, you could use video analysis and you'd be able to find the velocity of the rifle after and the velocity of the, or the mass of the rifle, and you know the mass of the bullet. Just from this video, you'd be able to calculate the theoretical velocity of the bullet leaving the rifle. Okay, I'm not going to solve that problem. I just wanted to show you how you would set it up. Okay, in physics, the most important thing is learning how to set up the relationships and then plugging in the variables. Okay, so this, applying the conservation of momentum, is a very useful tool in a problem to be able to calculate the velocity of an object after an explosion or after a collision. Okay, and you have to know how to set these relationships up. Okay, and then the last thing is, how do we calculate the force acting on the couple? Okay, well, we got to remember the impulse momentum relationship. And the impulse momentum relationship looks like this. F times t is equal to m times delta v, which means that my impulse that I'm applying, the force times the time that I'm applying, is equal to my change in momentum of that object. Okay, so the momentum of the bullet here is 0 to begin with. The explosion, the gunpowder, is going to apply a force for a certain amount of time to accelerate that bullet out of the nozzle, okay? And then we will get a change in the momentum, all right? So to solve for what is the recoil force, how much force is being applied, I have to rearrange this equation, okay? So the recoil force is going to be equal to the mass of the bullet times its change in velocity over the time at which the gunpowder is acting on the bullet, okay? So I would need to know the time, either from a graph or for some, they would tell me in the problem how much time the force was acting, and then I'd be able to calculate that force. So we would know the mass of the bullet. You would be able to measure the change in velocity from conservation of momentum, okay, from that, or they would tell you in the problem or through a graph. And the time would be something that they would have to give you, and then you'd be able to calculate the force. And from that force is equal to the opposite, the recoil force, the force that's pushing back on the object. So if I had a bullet that was 0.025 kilograms, 25 grams, let's say that's about right for a bullet, and the change in velocity is like, let's say it launches really fast at like 1,100 meters per second. That would be a very fast bullet. I bet you it goes half that speed, but let's imagine it's a powerful gun. And let's imagine that the time at which the explosion occurs is 0.1 seconds. I would say that's a relatively slow explosion. Okay, if I multiplied and divided that all together, I would be able to calculate the force acting on that guy's shoulder, which obviously looked like it hurt. Okay, next, sometimes what they like to do is they don't like to give you this in numbers. What they would do is they would give you all the data in the form of a graph. Okay, so what does the data look like in the form of a graph? So what they would do is they would give you a graph of, let's say, force over time. And if they had a sensor inside of the gun and it looks something like that, okay? And let's say that's 1,000 or 10,000 newtons, okay? Over here, all right? Let's say that's like 0.01, this would be 0.02 seconds, okay? That graph, you should be able to interpret and understand a few things about this graph. Number one, the time at which the force is acting is going to be that time between the start of the force and the end of the force. That's 0.01 seconds, okay? Whoops, I should have said 0.1 seconds, but that could be 0.01 seconds. Okay, and the other thing you need to understand is what the area under that graph means. What would the area under that triangle represent of a force time graph? Okay, well, the area is going to represent impulse, okay? Because anytime you look at the area under a graph, what that means is you're multiplying the axes together, okay? If I'm multiplying the axes together, force times time is impulse. And force times time under this graph is the area under that triangle. So I would have to use some algebra, okay? Or not algebra, but just some geometry to measure what the area under those triangles represent. And then calculating that area would give me my impulse. If I knew the mass of the bullet, I'd be able to calculate the change in velocity. And that's what we would do when you're using graphs, if you remember, okay? So just to summarize, when we're calculating recoil forces, they can give you the data in the form of numbers, okay, from a diagram, and you'd have to use conservation of momentum to calculate the velocity of a bullet. And then after calculating the velocity, you would then use the impulse momentum relationship to calculate the recoil force, or they would give you a graph, okay? And then from the graph, you would have to calculate the impulse, and from the impulse, then calculate the velocity or whatever they want you to calculate, okay? So know how to use graphs and know how to use the formulas. In the next video, I'm going to talk about a problem of a water hose, if you remember, and calculating the recoil force when water is ejected from a hose.